just very quickly, can I define a function? So in R, that means the easiest way is typing fun. Let's do it again, fun. Take the first suggestion, so just tab. And that's telling me, it's asking me for 3 items. What am I going to call the function? Let's call it f. What are we going to call the variable? Let's just call it x. And what does the function actually do? Shall we take maybe a quadratic one? So x, why don't we take 0.05 times x squared, and this hopefully works. Yeah, so you can now see in your environment, we have the function f. It's dependent on a single argument, uppercase x. Now I can type f of, for instance, 60, and that didn't work, did it? Should have I typed x over here? No, that should be fine. So what is the issue? Is the issue maybe the way I've just defined it over here? Is it just a case of wrong syntax? Object x, right. This is uppercase, yeah? That's uppercase. Yeah, so as a rule of thumb, when something goes wrong, very often it's the lower versus uppercase situation that I've just found myself in. So now that we have an f, and I'd like to flatten it slightly, or well, subjective whether it's slightly. So f of 60 is 1 atome. And shall we stick to the 100 observations that we had 2 sessions ago? That was the Sunday session when we met for 2 hours. Really our first session where we were working with R, at least ever since we started working with this book. Although maybe I'd like to change things slightly. Back in that session, we had 100 variables, but they were very neatly. The first observation had an input variable of 1. The second observation, an input variable of 2. And I do appreciate that may lead to certain misconceptions. So is there a way? I think there is, but I'm probably going to struggle with this, where I can kind of randomly generate. Let's see. Randomly generate 100. Let's have a look. Do I need this? And this has not worked. Replace. Yeah, you need to type true, not did I just type yes? Look at this. This is maybe more closer to what you would expect in a practical situation, where all I'm saying is the first observation has an input of 60, and we were saying that we would think of our input as age. So interviewing a 60-year-old, a 46-year-old, a 65-year-old. If you're asking, if it wasn't entirely clear from, and I'll save it as our x age variable. And now the numbers have changed because I ran it a second time. If you want that it's always the same, if you want that when you generate 6046, that when you run the code a second time, and this was what Excel was doing in that 2-hour session, each time you paste numbers, you add a column, it generates it generates the data each time, and that's a probability distribution. So you're not guaranteed that what was generated previously will necessarily be generated again. However, in R, I don't know if there's a way of doing it in Excel. Given what we know about Excel, I'd be surprised if there wasn't some way of doing it. You can have a line that says set seed, and I'm just going to write, for example, 150. Now that 150 is just a label. I could do it set 1. All it's doing is that, without going into too much detail, when I generate these input variables, they should always be the same. So look, 57, 88, you need to look at my console, 57, 88, 53. If I run it again, I'm expecting that R generates. It's true that it's generating randomly, but it's going to generate, for reasons that we're not going to go into, the same values. Should have I maybe set seed this, and then I do it again? Yeah, see, they're the same. 68, 39, 1, 68, 39, 1, all the way to 29. This is extremely useful if, for example, you're following a textbook, and to my knowledge, this gives us an excuse to already look at the text. When we start the R code, because yesterday when we were, yeah, I spotted this yesterday, set seed 1303. Think of it as a key, and if we're using the same key, then these 50 randomly generated normal distribution values will always be the same and will agree with the textbook. So it's usually you will see this, so that if you're trying to replicate something, you can very easily see, do I have the same values as the book? And if they're not the same, and I'm using the same seed, then clearly something's gone wrong. Well, there's always the off chance that there's a typo in whichever book you're using. I'd be really surprised to find any typos in this book. So far, we've developed quite a high opinion of the material that we're using over here. And I can show to you in RStudio. So we're taking a seed of 1303, and we're going to generate 50 random values. But when we say random, what kind of shape? They follow the normal distribution. That's like a bell curve. If you've ever seen maybe test scores or IQ scores, that's the famous one. It's a bit controversial. IQ scores have been used for quite nefarious reasons. For example, stopping certain sections of society to vote in certain countries. And we should have the same values. Let's at least look at the first one, 1.1439. And we have the same one, 1.14, rounding to, is it 4 decimal places? So I'll do it this way. I think there's in the sort of in the overall environment. I'll just do it this way. Yes, question?
What does set seed mean?
Beg your pardon?
What does set seed mean? Set seed.
Yeah. What does it do indeed, right? All you need to know for the time being is, actually, I'll go a step further. R or RStudio, strictly speaking, although I don't want to go off, stop me if I'm going off at a tangent. The numbers it generates when you use a distribution like what I did over here with sample or with normal, although they look random, strictly speaking, they are what we refer to as pseudo-random values. Now, what does this mean? Well, this means that R doesn't actually generate random values. For all intents and purposes, they are random, and we will take them as random. But strictly speaking, what R has, and this is kind of getting into we're looking under the bonnet. Strictly speaking, it has pre-built into it these randomized lists of values that when you call them, R actually knows what it's going to give you. So although it looks random to us, if you're in the underlying code of R, you can actually know exactly when you run a function like the normal distribution or the uniform distribution, or we mentioned the binomial distribution yesterday, heads, tails, 50-50, maybe 40-60 if it's a biased coin. R actually knows what it's going to give you. But like I said, for all intents and purposes, where we're concerned, where the user is concerned, you may take them as random values. The reason why we use set seed is that I can now compare my outputs to the book's outputs. I've picked this page randomly. And if the book generated these 50 values that follow the normal distribution, the bell curve distribution, then our values are identical to the book's values. It's just a really great way. In fact, why even explain anything? It's right in front of us. Sometimes we want our code to reproduce the exact same set of random numbers. We can use the set seed function to do this. Give it an arbitrary integer argument. This number, there is no interpretation of that number. Well, I could maybe say there is, but really just think of it as an arbitrary integer. We use set seed throughout the labs whenever we perform calculations involving random quantities. In general, this should allow the user to reproduce our results with a caveat. It depends on the version of R. So different versions, and if you'd like to know which version we're using, I think the quickest way, if you're seeing my cursor, is just looking at the number over here. So in RStudio, I'm using, when we first met in summer, I think I was on the 4.0. This is 4.2.1. I downloaded it last week, so it's the most up to date. It's probably what you all have if you've only put RStudio on your PCs recently. We're probably all using the same version. So going back to what I'm saying over here. Last whenever, I may have given the wrong idea. In fairness, I was following exactly what the book did in its diagrams, and the book has very good reasons for doing so. But I may have given the wrong idea that a raw data set, you're going to expect that you're going to have inputs that, first of all, increase with the same increment, with an increment of 1 in this case. And secondly, demonstrate no repetition within the data. Now that's usually not the case. So what I've done, since I'm not using any actual raw data sets, this is what I want to get to though eventually. So with enough, once we've done a good amount of sessions, then I want to start looking at papers. So I'm referring to peer-reviewed research papers with applications, and I'll usually take closest to my fields of, should I say expertise? My fields of expertise. So I'll take them from, for example, property and casualty insurance, or finance, or education. Usually those are the ones that at least I'm most passionate about, to put it that way. But for the time being, since we're not using any actual real life raw data, why don't we do something? Why don't we do something? And what I've done is to very quickly just generate some fake data. I've told R, hey, listen, take my X variable, which 2 days ago was the input variable. It was the horizontal axis in the book. Horizontal axis in the book from 0 to 100, although the book isn't necessarily taking 100, might be doing them in increments of 2 or whatever, so it may have 50 data points, but we had taken 100. And I'm saying, can you make it look more authentic? And I'm going to take a sample, but to lock in that sample, just in case maybe I decide to run the code again. And since I want that, I'm always getting the same values, otherwise it may confuse me or one of you. Let's take a set seed of, for example, 523, again, totally random. What would sort of be less random to a certain extent is now these ages that I've generated over here. And if you want to look at the distribution, you do hist x age. And now this is we're going to pretend that this is our raw data. And our raw data is saying we seem to have 10 buckets from what I'm seeing over here. We have, and just think of them as ages. The least represented age is the sort of the teenagers, right? The tweens and teenagers. We only have we have 4 of them apparently. The most represented data is the 30 to 40-year-olds. Now, that's your input variable. And do we remember this black curve? This black curve is when I start throwing out words like God and omnipotent. Let's say we know the relationship, and the relationship is this. So now I can create the Y output variable. Now, how do I do that? It should be really easy. I just say f of, actually, speaking of easy, I don't know whether it was yesterday, I actually said that this shouldn't work, but it does work. So why did I say it shouldn't work? Because this is actually just a number, and I've just given f a vector. R is extremely intuitive to use. We've avoided a loop over here. You'll often hear me saying this. The way R works, the way it interprets and compiles our lines of code, it immediately understands, and it will always do this. So if we didn't want it to understand it this way, then we're in trouble. But it understood what I meant in this case, which was I want you to calculate the f of every h, and we can plot it, and this can be our raw data. But now you would like me to include an error term. The error term, till this point, we have always cited it as that component of reality that isn't captured by the variables that our model is looking at. And I think it was yesterday where I said, you may have 1,000 variables. Very often when you're modeling, for a number of reasons, you wouldn't want to take every single variable. Most of them, in any case, would only have a marginal impact on the output, or better yet, they correlate. So it's pointless taking 10 variables if knowing one variable means that you basically know the other 9 variables. This was when I had said, if you know if someone is pro-choice, then you have a very good idea of maybe, I don't know, their religious affiliations, their age, etc., etc. Of course, the more variables your model does include, then you are adding more predictive power, but there's always this trade-off in statistics. Do I really want to include another 50 variables, meaning I need to send out more complicated surveys? Maybe I don't even know the data. It's out there, but it's not available to me. I haven't been collecting that kind of data. If it's only going to add, maybe increase my model's predictiveness, if that's a word, by 1%. Sometimes it might be worth if, hey, if all your competitors, remember, usually we're using these models to get some kind of edge over the competition, and it might make sense, but it does come at a price. It does come at a price. So let's plot. I need to save it as something. Let me just save it as yi. So these are my yi's. It's a notation we're going to use throughout the book for the output that you're predicting, as long as it's a model that is performing regression. Whereas I'm hoping that today we'll say, thus far, our discussion of model accuracy has been focused on the regression setting. Then there are also models that perform classification. But I wouldn't even mind. I'd like to do some of the book. I'd like to do some material. I wouldn't even mind if this session sees us just doing a quick recap. And I want to eliminate any misconceptions that arose maybe from just the way I've presented the material till this point. Let's minimize them as much as possible. So those are my yi's. So now what do I have? I have x. We're not going to use x any longer. It served its purpose. We have x age, and we have yi. Now we can plot. Please remember, there is no random error till now. Plot. Not like that, like this. Plot. And is it x age, comma, and now it's asking me for the verticals, so yi. So this is our plot. You should have expected a quadratic. It's the function I took over here. We can change it if you like, but let's stick to this for a second. Let's stick to this. Now we're going to include an error term. So I'm going to change yi. And how am I going to include an error term? It needs to be a random variable. We've been using epsilon for the random variable. And I'll do my best to repeat over these next few sessions. Just let me zoom in. Right. I'll do my best to repeat every session the following. Although, okay, well, now why didn't that work? Okay. I'm pressing the wrong button each time. Although it looks like a constant term, although it just looks like f of x plus 5, 7, 100, a million. That's a random variable. What is a random variable? Well, the one that you're probably most familiar with is the coin toss. That's a random variable, meaning what? Meaning it doesn't always give you the same output. It will either give you heads or it will give you tails. We don't know which output it's going to give us next. What we do know is the probability distribution, or we assume to know a probability distribution. If we agree that the coin is a fair one, then it's a 50-50 heads or tails output. In this case, what I'll take as my error term, what I'll take as my epsilon is I'll use the normal distribution. Now I need to write R in front of it. There are other letters. You could write P, you could write D. Those all give slightly different things. I wonder if we could get the list. I doubt this will give, but I'm looking for question mark on my keyboard. And if I run this, yeah, there's D norm, P norm, Q norm, and R norm. And this entire explanation, well, it's somewhere there, isn't it? I'm going to use R norm. R generates random values that depend on the normal distribution. And I'll use a histogram, which is one thing that yesterday's session could have really benefited from. So let's have a look. And yeah, no wonder I had a double R over there. So it's asking me number of observations. So let's take 100. What is the mean? The mean is 0. The mean is 0. You want that your error term has a mean of 0. So that, let's see if this is correct. So that half your data points, roughly half your data points will be above the black curve and half of them will be below. Now you need to specify the standard deviation. So most of yesterday's meeting centered on this concept of the variance of a random variable. Every random variable has a positive variance. So what if the variance was 0? If a random variable has a variance of 0, then there's nothing random about it. There is no variability. It's always going to give you the same thing. So for instance, we say that in a certain I don't know, take all the Facebook accounts, that should be in the billions, right? And we say that all accounts have the same number of photos uploaded by their respective users. It's clearly not the case. But over there, just take this as an example. There is no variance. There is no variance. So you're not going to model it with a random variable. If you know that every Facebook account has the same number of photos uploaded to it, then you know in relation to that specific variable, you know what it is for every account because it's the same for every account. I'll take a standard deviation of 1 for the simple reason that the book, although we could change it, now we'll see. Let me set the seed as well, and we'll take whatever 1, 2, 3, 4. Run it, and this is the error term. There are 100 error terms, and what I'm going to now do is I'm going to create uppercase yi, which is going to be yi. Remember, yi is the f of x plus epsilon. And now we'll plot it, and hopefully you know what to expect, roughly. Okay, so now we'll plot x age and uppercase yi. You're not seeing much of a difference, are you? Yeah, that's correct. That's correct. So why don't we take a more significant standard deviation? Why not take 10? Okay. So do we see what the error term is doing? It's removing the determinism. What do I mean by determinism? Over here, should I put it that way? Yes. So over here, we're saying that the output depends only on the age. And although we've ignored other variables, they don't matter. They don't matter whatsoever. And maybe I'll take a larger standard deviation. Let's take 20. Now we have this data. This is going to be our raw data. This is going to be our raw data. I could create a data frame. Is it cbind? This probably won't work. I think for this to work, you need it to already be a data frame. But we're going to see, aren't we? Yeah, that works. Okay. Is it a data frame? So let's call it my data. My data. And let's ask R what it is. Okay, it isn't in fact a data frame. It is a matrix. There is a way to save it as a data frame. You might be asking, what is the difference between a data frame? Really, one major difference is that a data frame, you don't need to have the same type of data. So you could have some columns that are text, others that are dates, others that are numeric, whereas a matrix, although it's saying matrix and an array, not entirely sure what that means. Is it saved somewhere? Yeah, so my data. And over here, it looks like just normal data, but it's not a data frame. I think there is a way of doing it. My data, I think as data frame, my data. And now it's a data frame. Now it's a data frame. In fact, you'll notice if we scroll up, you can tell that this is a matrix from the rows. It is row 1 and comma nothing means all the columns, all of them. Row 2 and the nothing means take all the columns. If we did 3, 2, then that would be specifically referring to this one. Okay, so we now have the data as a data frame, So you could start asking, you could do, for example, summary. For example, this may not have worked while it was saved as a matrix, but it should definitely work now that I'm using, what's the word? Now that I'm using a data frame. And it's giving us, I usually refer to these as like secondary school statistics for each field. So you have the age field, there's your minimum. It's subdividing the data into quartiles. So your youngest 25%, youngest since I'm just taking this to be age, your youngest 25% is 33 years or younger. Your oldest 25% is 76 years or older. Now, what are we going to take? What are we going to take these to represent? Due to the variance that I took, due to the standard variable, we even have some negative data. Anyway, it is whatever it is. It's not that important. It's the output variable. It's the output variable. Right. Now, where does this leave us? Well, why don't we now model it? And we said yesterday the least flexible model, but it has so it suffers from lowest flexibility, but as a trade-off, I think there's something, was it bias that we mentioned yesterday? I think it was bias. Is a linear model. And I could do LM, linear model. Now it wants a formula. I'm going to say the outputs tilde depend on the X age. Now what else does it want? It's asking for the data. I'm going to say my data. And we can ignore all these, but look at, well, not those, but look at how these are things that you can specify. For example, weights. Maybe you could have the model, instead of treating all the data, each data observation in the same way, it may assign a higher importance to some of them. I've never used it. Don't ask how to do it, but at least from the looks of it, you would be able to do something like that. Now we have this, and we've just created the model. Now let me see, how would I plot it? How would I plot it? So all we need is 2 betas, right? Do you remember our betas? When we first started these sessions, do you remember the betas? So this is taking 2 variables, so it has 3 betas, your y-intercept, your beta 1, which would be associated with the education data, and beta 2 with the seniority data. Now, how do I get an orange line like the books? So far we have the raw data, but we'd like to create this orange line. And we could also calculate the MSE if there's enough time. We may decide that we do no new material this session. We're going to have to do this from time to time. I don't want anyone to kind of like get discouraged or fall behind. I'm not necessarily doing a good job, but I am trying my best. But each session I'm realizing there's always that one item, or at the very least one item, where I realize, okay, I definitely could have explained this a lot better. And speaking of explaining it better, I didn't show you the histogram of the epsilon. It's going to resemble a bell curve. Epsilon. What do we mean by bell curve? Not a very good bell curve. I was expecting. I wonder if I have something wrong. Beg your pardon?
That's the normal distribution.
It should be, but there are only 100. Had I taken maybe 1,000, although it looks pretty odd, I think it's fine. Had I taken 10,000, let's do it that way. Had I taken 10,000, and I had a chat with one or more of you today about 10,000. Let's call it epsilon 2, and we'll say 10,000, and we'll plot it. Not plot, beg your pardon. Histogram. Histogram is just bucketing by frequency. Histogram. Those of you to whom I've sent the CT3 notes, chapter 1 is all about histograms. Look, do you prefer this now? Doesn't this look like a bell curve? Yes. Yeah, you bet. And the more observations you take, the closer it should converge to sort of the theoretical shape. Okay.
So you're putting epsilon against frequency.
Yeah, so forget about epsilon, because now it's epsilon 2. I just took 10,000 observations.
Okay, okay.
So with only 100, especially the standard deviation, I took quite a wide standard deviation. It kind of, you don't have enough data to really get a good idea of the shape of the underlying distribution. With 10,000, you're moving a lot closer to expecting to generate something that is closer to the theoretical shape.
Mm-hmm. So the more you have, the more accurate it would be.
Yes, yes. And you know, you can even prove this rigorously. There are entire results in statistics. On the job, they're not that important, but it's worth, especially when you're still young, that's the time to at least go through one or two proofs. It does help.
Thank you.
Okay, thank you. So this is the summary of my data. You can look at the first few. You can look at the first few entries. And what we're doing is we are pretending. We're pretending. This will never happen in real life. We're pretending that we know the relationship, but now forget about that, and pretend that this raw data wasn't generated in any way, but you have collected it. You have collected it. So you have interviewed 100 people, and we said X can be their age and Y is who cares. And they give you your age, they give you their age rather, they give you their YI, whatever it is, savings, for example, in their current account, you name it. And now this is your raw data. Now you want to fit a model. And we're taking a linear model. That's the LM function. So I should have a Y equals MX plus C. I should be able to create a function, and we'll call it F hat. Call it F hat. If I give it the age, and this is just a dummy variable, I could call it Z, I could call it whatever I like. It should give me an MX plus C, right? Y equals MX plus C. And I could either just copy, I could either just copy these. I could do it this way, which is a bit, you know, you wouldn't want to do that. So instead you do $ coefficients, and you say 1, and I'm going to call that my beta naught. And I'll do exactly the same thing. And I'll call this beta 1. I'll take 2. Now I'll say beta 1 times X plus beta naught. This is the model. This is the model. Now, so it's not going to do anything, but it's saved. But now what I can calculate is I can calculate F hat of my, and these will be the Y hats. These will be Y hat, I. This is the model's predictions. This is the model's predictions. Beta naught is not found. Did I not run this code? Okay, now that seems to have worked. And now I may plot. There is a way of doing them on the same graph. Now I may plot X age against Y hat I. Ta-da! So that's what the model is predicting now. So I'm going to have to switch between, I think I can just use these arrows. So this is the raw data. This is the raw data. And we've taken a linear model. and this is your predicted data. So now what you could do is you could calculate the mean square error. How? Well, it is the mean. So I need to divide by 100. I'm hard coding, you should never do that, but 1 on 100, the summation of y hat I minus y I squared. That's your mean square error. It looks awfully large, 1978. So who knows? I may have done something wrong over here because it looks larger than I was expecting. You could see this for a specific. So let's say you want to see the mean square error, not the mean square error, the square error. Let's say you want to see the square error for the 80th observation. All you do is this, square brackets and 80. And it's 4171. So what does that mean? That means if I square root that number, that's the difference between the prediction, so the y hat, and the actual output. There's a difference of 64. Right. So hopefully you found that useful, and we've dispelled. Please ask.
So,
yes.
So that's the mean squared error. Why?
The mean squared error is this.
Why
It's
something different?
the mean squared error is a single value that you calculate for each model. Each model has a mean square error. Now there's the training mean square error, and there's the test mean square error. Now, very often in practice, you will not be able to calculate the test mean square error because you just won't have, very often your model is trying to predict the future where you just don't have that future data. So what I've done over here is I've calculated the training mean square error. So it is of the model, and I've taken a linear model based on the very same data. So the mean square error that I've calculated is based on the very same data that I used to create the model.
All right. Thank you.
Excellent. Excellent. I don't know if there's anyone else who would like to chip in. So let's clarify this. Every other sentence of mine usually includes one reference to the word model. We're no longer at secondary school or post-secondary sixth form, where we are given a function. That's number one. In real life, you're not given the function very often. I mean, you do have many functions. If you know that visiting a certain park has a fixed fee of 50 euros, and every duck that you feed is going to cost you an additional 10 euros. That's a model. That's a model. That's a purely deterministic model. So there are certain things which are purely deterministic. Entrance fee, 50 euros, 10 euros per duck when it comes to feeding. So if I feed 4 ducks, that's going to cost me 90 euros. That is purely deterministic. And even then, maybe if you're really good at negotiating or you're quite charismatic, you could maybe negotiate while you're at the park and bring it down from 90 euros. You tell them, come on, I'm going to feed 4 ducks over here. Give me a discount. And depending on the park, if it's, if they don't have maybe necessarily an electronic system, which is quite rigid, but if it's just, they're handling cash, then you can haggle with them. See, that's now a third variable. So the first two variables were the entrance fee and the fee per duck. So that's a purely deterministic model, and you're assuming that you know F, but very often you don't know F, or actually I shouldn't have even said that. Maybe F. No. F isn't the whole story. That's what I should have said. F isn't the whole story. There is the error term. F is only allowing for certain variables, the entrance fee and the price per duck. Then there is the error term. Maybe it's a machine. Should I underline it? Not really, right? That maybe it's a machine that doesn't give you any change. So although it's 90 euros to feed 4 ducks, if you feed, I mean a literal machine over here. I mean a payment machine. If you feed it 250 euro bills, it doesn't give you any change. So that 90 euros was wrong. It has cost you 100 euros. So that's the error term. The error term is telling you your X isn't allowing for other contingencies. Now, how does that fit in with what we've just done over here? We have the raw data, and we would like to fit a function to it to make predictions, to understand the relationship between the variables, etc., etc. This is a regression model. I did say I'd like to, and we're fast running out of time, but I'd like to maybe at least read the first page for classification models. But just before that, you have your data, you want to fit a model to it. Now your model is F hat. Whenever you see F hat, that is your model. Strictly speaking, you probably want some kind of epsilon hat as well. So you want to determine these two things. Your F hat, which is usually an algebraic, many times it's an algebraic expression, it's an algebraic relationship. You are describing reality using algebra. We took beta 1 times x plus beta naught. And then there's the error term. Now let's finish off with this page. The classification setting. Thus far, our discussion of model accuracy has been focused on the regression setting. But many of the concepts that we have encountered, such as the bias variance trade-off, transfer over to the classification setting with only some modifications due to the fact that yi is no longer numerical. So this is classification, where your yi, your y hat is predicting in which group something should be classified. So one of the very first examples I ever mentioned over here was in the case of insurance, is a claim that hasn't been settled yet going to go to court or not going to go to court? That's a classification. Suppose that we seek to estimate F on the basis of training observations, which we're indexing from 1 to n, where now y1 until yn are qualitative, meaning forget about subtracting in such a situation. Well, what we've done over here for quantitative data, where we're looking at differences as just subtraction, and yes, then we square, etc., to get the mean square error. We can no longer do that. The most common approach for quantifying the accuracy of our estimate F hat is the training error rate. So we're no longer going to discuss the mean square error for classification models. Now we have the error rate. So we're still speaking of training error rate, and I would imagine there's going to be a test error rate somewhere along the line. This is the proportion of mistakes. Now, what is a mistake? Well, that's when you incorrectly classify something. The proportion of mistakes that are made if we apply our estimate f hat to the training observations. So where does the proportion come in? This is the numerator, and it is as a proportion of this denominator. So worst case scenario, every single prediction is wrong when you compare it to the data, and you would have 100% training error rate. 100% training error rate. Now, how do you get this 100% training error rate? Well, that would be if the pink is n, and can the pink be n? Yes, because this is going to be either 1 or 0. This term for every observation, so think of our 100 observations today, for every observation, this blue term, let's read it. Here, y hat I is the usual predicted class label for the ith observation using f hat. And this is the notation now, this new notation. Uppercase I, that just stands for indicator. And it is equal to 1 if you got it wrong. And it's 0 if you got it right. So if you've classified correctly, that's 0. It doesn't contribute to your error rate. If they're unequal, then that's a point against you. You need to look at this one as 1 point against you, against your model. Yeah, so if it's 0, the ith observation was classified correctly by our classification method, by our model. Otherwise, it was misclassified. You either got it right or you got it wrong. Hence, equation 2.8 computes the fraction of incorrect classifications. Equation 2.8 is referred to as the training error rate because it is computed based on the data that was used to train our classifier. As in the regression setting, we are most interested in the error rates that result from applying our classifier to test observations that were not used in training. The test error rate, it's exactly the same calculation, but it's going to use data that has not been inputted in the creation of the model. The test error rate associated with a set of test observations of the form x naught, y naught is given by this. So what it's telling you is take all your test data. It just refers, the book, I'm not entirely sure why, it just calls it x naught, y naught, but you could have, I don't know, 1 million test data points. For some reason, I either just so it doesn't use a different n, but it's the same thing. AVE is just average. Again, I'm not 100% sure, but it is the same formula. It is the same formula. It's just using, instead of the training data, which is the I observations, is just using these y naughts. But plural, please, plural. Where y naught is the predicted class label that results from applying the classifier to the test observation with predictor x naught. A good classifier is one for which the test error is smallest. Just as a preview for tomorrow's session, it is possible to show, though the proof is outside of the scope of this book, that the test error rate, this, is minimized on average by a very simple classifier that assigns each observation to the most likely class, given its predictor values. In other words, and we'll probably have to explain this notation tomorrow, we should simply assign a test observation with predictor vector x naught to the class J for which this is largest, please tell me that you haven't understood anything. We'll start with this tomorrow, but just very quickly, this is just probability of this, meaning the blue is going to be at the very least 0, at the very most 1. The J is all the different possible the J is each possible different classification. So if it's a very simple binary classification model, either goes to court or does not go to court, J, you will consider all the possible J's. So one of the J's goes to court, the other J does not go to court. And this vertical line simply means, and probably best thing is to read the entire thing, the probability that the class label, you're predicting the class label in a classification question, in a classification problem. You're not predicting wage, you're not predicting height, you're not predicting interest rates. You are predicting the label. What do I mean by a label? So for instance, goes to court, does not go to court. Let's keep it simple, let's keep it binary. Or for example, I lend you 10 euros, you default or you do not default. You either pay me the 10 euros back by the agreed date or you don't. Obviously, there are still gradations. I mean, do I really mind if you paid me a day late? Or do I really mind if you didn't pay me the 10 euros, but you paid me 9 euros 90 cents? Maybe yes, maybe no, but there are gradations. But binary is the simplest. You either paid or you didn't. Given that, and this is where we're conditioning. This is where we're conditioning, and we can, can have a lot of fun with these next session, which will hopefully be tomorrow. Given that the input has these characteristics, I don't know, age, sex, religion, you name it. It's actually one of the simplest things that we're going to do in all this course. Do not let it intimidate you in any way. Which means I appreciate we kind of took a deviation today, but I strongly feel that we needed this recap, and we've still managed these last few minutes to do a quick preview of what to expect tomorrow. A lot of it is just going to be repetition. The diagrams are slightly new, but once we get those done, the rest of this chapter is just R, probably the easiest part of what we're going to do these next few sessions. And I have been saying I would like us, and we could even perhaps assign some of this as homework in inverted commas. We'll just one of the questions perhaps. Maybe I could try working them in advance. From that point onwards, each chapter is going to be a specific, to my knowledge, each chapter is going to be a specific family of models, starting from linear regression. So the things that we're going to see over here are linear, and this is going to be great fun. This is going to be, look at this. This is where you're looking at multiple variables. You're looking at, let's say you want to predict, I don't know what we're trying to predict over here, but a diagram like this is giving you all the patterns. So for example, so these are the variables. By the way, the upper triangle and the bottom triangle should be identical. Maybe just, yes. So this is the same as this. Maybe not. Maybe they're reflected in the y equals x, in the y equals x line, but they're probably the same. So for example, this would be this, or I think there is like a 45, it would be 90, I think, right? Not 45, a 45-degree rotation. And you're looking at all the different relationships. For example, over here, we're looking at cards. I'm not sure what cards means, but cards against, I think it's against balance. This is cards against age, cards against education, etc., etc. So this is where we'll start taking, we'll seriously start taking multivariable data sets into consideration.